afternoon. My name is Jean-Louis Briot. I'm the president of the Geo-Institute and a professor at Texas A&M University. Welcome to the 2009 Karl Terzaghi Lecture. This is the top highlight of our year, and we again have an outstanding recipient. Before we go on, I believe we have some past recipients of the award with us tonight. Would they please stand and be recognized? Now let me call on IFCEE President-elect Blaine Leonard to give the award to Clyde Baker. Blaine.
Thank you, Jean-Louis. It is indeed a pleasure for me to be here tonight to present this prestigious and scholarly Terzaghi Lecture. Instituted by the IFCEE Board of Direction in 1960, the Terzaghi Lecture now is administered by the Geo-Institute in honor of Karl Terzaghi. Annually, the Geo-Institute Board of Governors recommends a distinguished engineer to deliver the Terzaghi Lecture. The 45th Terzaghi Lecturer is Mr. Clyde N. Baker, Jr., P.E., Distinguished Member of IFCEE of AECOM Technology Corporation. Our speaker tonight has clearly shown the expertise, innovation, and commitment that match the example set by Karl Terzaghi and the other distinguished recipients of this award. I would like to ask Mr. Baker to now join me at the podium. Mr. Baker, in recognition of your significant contributions in the design, analysis, and construction of deep foundations for high-rise structures around the world, I would like to present you with this award. I very much look forward to your lecture this evening, and now I appreciate your leadership in the profession. Turn the time back over to Jean-Louis.
Thank you, Blaine. Now it's my pleasure to introduce to you the 2009 Karl Terzaghi Lecturer, Mr. Clyde Baker. Clyde Baker Jr. grew up in Flushing, New York, son of General Surgeon Clyde Baker Sr. and Muriel S.T. Baker. He graduated from Flushing High School and received his BS and MS degrees in civil engineering from MIT, and a BS degree in physics from William and Mary College. He joined the staff of STS Consultants in 1954. Over the last 55 years, he has served as the geotechnical engineer on many high-rises in Chicago. 8 of the 20 tallest buildings in the world, including the 3 tallest in Chicago, Sears, Hancock, and Amoco, and the current 4 tallest buildings in the world, the Petronas Towers in Kuala Lumpur, Malaysia, 101 Financial Center in Taipei, Taiwan, and Burj Dubai in Dubai. He is currently working as a consultant on several super tall buildings currently under construction, including the Spire in Chicago, Doha Convention Center and Tower in Qatar, and Incheon 151 in Incheon, Korea. As a result of his experience, Mr. Baker has developed an international reputation in the design and construction of deep foundations. He has been a leader in using in situ testing techniques correlated with past building performance to develop more efficient foundation designs. In the Chicago soil profile, this has facilitated economical use of belt caissons on hard pan for major structures in the 60 to 70 story height range, which normally would have required extending caissons to rock at significant cost premium. Mr. Baker credits his success to his early university teachers who taught him how to think, including Donald Taylor, T.W. Lamb, Hal Aldrich at MIT, Karl Terzaghi and Arthur Casagrande at Harvard, Ralph Peck, George Osterberg, who are known to combine theory and practice. Mr. Baker is the recipient of the DFI Distinguished Service Award, the ADSC Outstanding Service Award, IFCEE Thomas Middlebrook and Martin Cap Awards. He is an honorary member of IFCEE, has served as chairman of the Geotechnical Engineer Division of IFCEE, what we now know as the Geo-Institute, and is past editor of the Geotechnical Engineering Journal. He's a member of the National Academy of Engineering and was the past recipient of the Ralph Peck Award for 2000. More recently, he received the 2007 Engineering News Record Award of Excellence and the 2008 ASCE Opal Lifetime Achievement Design Awards. He really collects the awards. Mr. Baker is a past chairman of STS Consultants, a 550-person engineering firm headquartered in Illinois, and currently serves as Senior Principal Engineer of AECOM Technology Corporation. On a personal note, he gives most credit to his wife of 53 years, Jeanette, for their happy marriage and their flourishing family of 3 children, 6 grandchildren, and 2 great-grandchildren. For relaxation, Mr. Baker says he likes to read and to run, although very slowly, and to kayak on Lake Champlain, where his family has a log cabin. Travel, where he can visit and reminisce with old friends, is also high on his list. The title of the 2009 Terzaghi Lecture is Uncertain Geotechnical Truth and Cost-Effective High-Rise Foundation Design. Please welcome the 2009 Terzaghi Lecturer, Mr. Clyde Baker.
Thank you, Jean-Louis, for that very generous and cost-effective high-rise foundation design. And when I gave a draft of this talk in our office, one of the senior engineers came up to me afterwards and said, "What you're really talking about is performance-based foundation design using empirical methods correlated to your experience." I said, "Yeah, I guess that's what I'm talking about." Well, there it is. The only thing I could add there is the judgment I'm going to talk about is not, it's judgment based on experience and not necessarily rigorous statistical analysis. Most of you who know me appreciate that. The major portion of my career has been spent in Chicago, and the Chicago foundation history has undoubtedly been an influence on my development as a foundation engineer. I followed Ralph Peck in Chicago and gained from Peck's experience greatly, I would say. And Chicago is, I want to give a little of this because, like I say, it helps explain me a bit. Chicago is a glaciated area. We've been run over by glaciers over the last 40,000 years, maybe at least 5 times. And you can see the different till sheets represented here. And this is close to downtown Chicago. There's a sand layer over these till sheets that increase in strength with depth. This represents a profile of downtown Chicago on which we've shown not only the soil profile and the different water tables. We have 3 water tables. The bottom 2 water tables you want to take a look at because they come up in later case histories and they can cause all kinds of problems. Also shown on this profile are the kinds of foundations that have been used in Chicago. Up until the 1890s, I would say, footings and mats supported the structures that got as tall as 20 stories. Of course, when you put 20-story buildings on the stiff clay crust over our soft clay, you're going to get excessive settlement. And some of our buildings are rather famous for excessive settlement. The auditorium building has settled a maximum of 30 inches and a maximum differential of 18 inches. It did it gradually enough, and they maintained all the cracks, mortared them up and everything, as I understand it, so they kept it safe. But you can notice it when you visit us. You go in the auditorium, you actually step down as you go into the auditorium. This is just showing a typical point, not on the worst part of that, not on the 30-inch part, but you can see even over a 50-year period, there's 18 inches of settlement reported in this particular point. Now, because of this settlement, buildings in that time, they knew from experience that it was going to settle. So they built them a little bit higher, 3 inches, 4 inches. I think the maximum height was 9 inches. And of course, 30 inches is a lot more than 9 inches. So General Suey Smith developed what was called the Chicago caisson method. It involved digging a circular shaft and driving timber lagging sets and then bracing them with circumferential steel rings. And you just keep going deeper. When you get down to a hard bearing level, you can enlarge it, and you can call it underreamed or belled or whatever. Now, I love this picture. This is a picture down on the bottom of one of these hand-dug caissons. It must be a rather sizable bell. And you can see the workers. I've ridden up and down the muck bucket there many times with the workers, but I wonder how those guys in the back got up and down, the guys in the suits with the fedoras. And to be honest with you, I don't have the answer to that one. Now, what they started to do is put these taller buildings on the caissons down on the hard clay and hard pan. And the presumptive bearing value was 12,000 pounds per square foot, 6 tons per square foot. By the way, that is still the Chicago Code presumptive bearing value for hardpan, if you can believe it. Anyhow, long about 1919, D'Esposito, who was the chief engineer with the Union Pacific, they were building a head house, I guess they called it, and he decided they had better prove that the bearing pressure was good for 12,000 pounds per square foot, because that's what they were using. And this is a massive load test. This was probably the biggest load test at that time. And in those days, you know, the load tests went on and stayed on. This load test took a couple of months to run, and I think they got up to a bearing pressure well over 75 tons per square foot. And you know, they were pretty smart. This was really before modern soil mechanics, but they figured some of this load's got to be being carried in the shaft. So we better dig a tunnel down and dig underneath this thing, our shaft, mine it out so there's no bearing at all, and reload it and see what is carried in friction. So they did that, and when they subtracted that load off of the prior load, the bearing pressure that they put on the hardpan without failure, 65 tons per square foot. They were trying to prove 6 tons per square foot. Now, you'd think that would have led to a rash of construction with bells on hardpan and using higher bearing pressures. Unfortunately, now you probably can't figure out what this is. I took this picture down in a shaft that was having a lateral blow-in because the shaft had gotten too close to a rock caisson, and water and sand and silt was coming in. And what happened in those days is some owner decided, well, I got a super important building. I'm going to put my building down to rock. And when he did that, he's pumping water, he's moving sand and silt, and he's undermining the poor guy that's next to him on belt caissons. So the end result of that is that Chicago's big building boom in the 1920s, when most of the 20 to 40 story structures, maybe 45 story structures were built, all went to rock because nobody wanted to risk, if they sat on hardpan, even though you could prove a high brain pressure, somebody coming along aside and undermining them. Okay, now we move up to, nothing happened during the Depression, as you know, and post-World War, post-Depression, post-World War II, and we were still pretty simplistic. Pre-1948, I mean, the structural engineers were hardly any geotechs. The structural engineers would base their design values on the unconfined compressive strength, and so that was what it was. You had to have the unconfined compressive strength, and that was your allowable bearing. Along with the Terzaghi Peck book and others, bearing capacity theory, that got up to 1.2 to 1.3 times if you wanted to keep a factor of safety of 3. And then Skempton came along, as you know, and showed that in hard clay you could go up to 9. The ultimate was 9 times cohesion, factor of safety of 3 times cohesion, so 1.5 times the unconfined. For your allowable bearing. Now, when you got up to the really big buildings that we started to build, Lake Point Towers, I think, was the first really big one that I can recall that I was involved in. 65 stories, and loads were very high, and rock was very deep and very expensive to go to rock. So it was in part of Chicago with the deepest depth to rock. So there was big pressure to use belt caissons, and they actually wanted to use the highest bearing pressure they could. So we did triaxial compression testing, and we confirmed that you could use 30 KSF. Now this is now 2.5 times the code allowable, but with the triaxial compression tests, it was acceptable. However, you're still left with predicting settlement, and that was a little uneasy on predicting settlement. So we were very glad to see the pressure meter come to town. In the late 1960s, I think we were one of the earliest firms to have a Menard's pressure meter in general use. And Menard developed the pressure meter as a graduate student at the University of Illinois. And I look at it, my simplistic way, as kind of like it's analogous to an in-the-ground load test. You're radially expanding this probe against the borehole walls, and you're measuring the pressure and the amount of deformation. So it can be looked at that way. Now, some of these, I've got some, this is just a drawing that shows it, and I want to show it to show what's important to us. And we use the pressure meter a lot. I mean, we have found it very successful at predicting settlement in our glaciated soils. And I'm just going to hit on the high points that we look at. We always run an unload-reload cycle at the creep pressure. And we have the best guys doing it. They have 0 creep, 0 creep, 0 creep, starts to get a little creep, run an unload, reload pressure, and then you go up to failure. And what we have found that the alpha that Menard uses in his table, it's also used in Jean-Louis Briard's book, is based on his experience in testing all over the world, and it's okay for generic use. But we find that if we use the alpha, we have related it to the initial modulus E sub D over the reload modulus, and we have found that a very effective indicator. It varies with the soil type, and we have our own procedures. We don't use an alpha factor less than 0.5 in clay deposits. We don't use less than 0.4 in silt, and we don't use less than 0.3 in sand. And following that, we get very good settlement prediction results. And you'll see how important that is in one of the, unfortunately, few equations that I have in this talk coming up. But the rules that we use with the pressure meter, if we want to predict settlement as accurately as we have been doing in the past, is we want to keep the total pressures less than the creep pressure. So the dead load pressure plus the long-term real live load pressure plus the effective overburden pressure, we try to keep to less than the creep pressure. And that assures that our stresses are in the pseudo-elastic range. We have found that the creep pressure is analogous, very close to the pre-consolidation pressure of the soil. Bob Lucas, who used to be with our firm, did a lot of testing on that. Bruno Debussy from France also. We found the creep pressure to be very close to the pre-consolidation pressure, and we use that. Now, for the settlement theories, the two approaches that we use in our sort of empirical way, approximate way, we use the Menard method, the Menard procedures, which we'll see the equations in a minute, and we also use the elastic theory, where it's also an approximate. There's a formula for it, and it's approximate, but it gives you an elastic theory method and then the Menard method. The elastic method, the way we use it, usually predicts more settlement than the Menard, and you'll see why in a minute. And that's because of the alpha factor. If you look at the settlement equation, you'll notice that in one part of the equation, the alpha is an exponent. And you can see that if you're going to use an exponent less than 1, you're going to be predicting less settlement. So we have found it very effective, and we get much closer using it in following the Menard rules in our glacial deposits, and we've tried to use it around the world. Now you're going to hear why you have to relate it to your local geology. You can't use their same methods everywhere. And this is Menard's equation for determining the E sub b, which is on the left hand of the equation. We won't spend time on that, but it is another important aspect. And then the elastic theory. Again, it's an approximation because you're using geometry influence factors that have been developed, and then you're using an average modulus, an average E. And in both these prediction theories, it is assumed that the stress level is within the pseudo-elastic range, which in pressure meter terminology means, as I said, the total stress is below the creep pressure. And these are the charts showing those influence factors to go in the elastic formula. Now, this brings us up to more of the current time, and what I want to talk about is the pressure today for more cost-effective foundations. Of course, we get hired because the clients think that we can help them come up with more cost-effective foundations. The increasing developer role has just pushed that even further. Now, this puts pressure on the geotechnical engineers to push the edge in the state of practice. So we've developed some rules that we like to follow, and you'll see what's happened in our experience in one case where we didn't follow them closely enough. But in general, we've developed rules that will keep us out of trouble while we're evaluating new ideas for reducing foundation costs. The themes that I wanted to talk about is judgment required in evaluating geotechnical uncertainty and the risk involved with ideas for reducing foundation costs. The ideas I want to talk about are maximizing allowable bearing pressure. That's an easy one. Get the most out of the ground you possibly can that you're comfortable with. Use of mixed foundation systems. When I started in business, structural engineers wouldn't consider mixing foundation systems because they didn't have the confidence that in fact, there weren't any geotechs. The structurals did their own geotech, but they didn't have the confidence that they could predict what the settlement would be, and so they didn't want to mix foundations. Now we mix them all the time. Reuse of existing foundations. And then use of highly stressed piles as settlement reducers. And I'm going to be talking about two different ways here. One of them is rather unique. Well, they're both rather unique, I guess. Not as friction piles, but as end-bearing piles. Usually piles of settlement reducers, when you consider piles of settlement reducers, they're in the friction pile category, so that may be interesting. In all cases, know your local geology and building history. I think it was mentioned before, I like to correlate to existing performance. Nothing beats a major case history, a well-documented case history in your geology. I mean, nothing beats that. And another reason for knowing your local geology and your building history is that we may not know as much as we think we do. And as an illustration of this, I just talk briefly about what was used on Petronas Towers and using a similar parameter, but arrived at much differently by necessity and local experience, was used on the Burj Dubai. Now those Petronas Towers, I think, are maybe the third tallest, and Burj Dubai is the tallest. In the Petronas Towers case, we had hundreds of pressure meter tests. I think it was like 67 pressure meter tests. 2 full-scale load tests. And both the local geotech and we got together and we arrived at a modulus based on all that data of 250 MPa. In the Burj Dubai project, that was equivalent about to our average reload modules, and that's what we have used in Chicago. We found that we have to use a little higher value. If we just use the reload modulus, we're going to over-predict settlement. The ground isn't stiff enough, so in Chicago, if we want to use that method instead of the totally Menard method, we'll often bump that up to come closer to what's actually observed. Burj Dubai, on the other hand, the local geotech had experience, and they did all sorts of tests, both lab tests and a lot of pressure meter tests, and developed an assumed modulus about equal to 2.2 times the average reload modules. Factor of 5 different. So you can see the kind of trouble you could get in if you used one philosophy, carried it around the world, and didn't change anything. Now these are totally different deposits, and you have to look at that. On the Burj Dubai, very porous, poorly cemented sandstone, siltstone, that sort of thing. Very low density, very porous, and very poorly cemented. And on the Petronas Towers, badly folded, weathered siltstone, sandstone, weathered to very dense soil. Low counts in both cases about the same, averaging 100 or more, but just different geology, and you have to learn to correlate what you're using to the local experience. Okay, so because of this, we have developed certain essential requirements. If we're going to try and work at the state of the practice on a major project, there's one absolutely essential requirement. The structural engineer and the geotechnical engineer must serve as a team. They must have confidence in each other and communicate well with each other and with the architect and owner. Dan Brown this morning talked about design build, and he talked about the importance of the contractor. I should have on here and the contractor, because the contractor is obviously very important on these major projects. But this was, I do have in here a little bit further on about the contractor, but it's extremely important to have confidence in each other when you're working at the state of the practice. These are just common sense advices. I don't think anybody's going to disagree with any of these. Know and understand your local geology. Compare and calibrate to known case histories and similar geology. And the geotechnical engineer and the structural engineer should develop the exploration program together. I know lots of geotechs tell me, the structural engineer has sent us a program that doesn't make any sense. I tell them, get together with them. Develop a program that makes sense, that you're happy with, and that he's happy with. And then I always recommend performing simple bearing capacity and settlement analyses before you spend the money on more sophisticated finite element programs. I'm a heavy believer in the new stuff. I've got my own staff doing that. It's beyond me, but I like to instruct them to do the simple stuff, see what, get an approximate answer, then go to the more sophisticated. And of course, if you can perform instrumented load test programs to failure, too often they're not performed to failure for one reason or another, so you don't really know capacities. You don't really know ultimate friction, you don't really know ultimate bearing because you didn't run it to failure. You got a safe design, sure, you apply a factor of safety to what you did and it's very safe, but you don't know as much as you would if you ran it to failure. And then when operating at the limit of past experience, take small steps. If you're in an area like we are, we don't increase the bearing pressures anymore in Chicago because the city knows we predict the settlement very good. They don't want any more settlement. They know if we up the bearing pressure, we're going to get a little more settlement. So they've kind of set the bar now, even though we say, well, we could go higher, we could do this. They say, no, we don't want you to do that. So when you're operating at the state of the practice, you want to take small steps. And then it's always good, particularly if you have our history and you have occasional surprises that you have to deal with, is to have a what-if plan, a plan B. What if this happens? What are we going to do? Have it ready ahead of time. Don't stop the job and everybody pull their hair while they try and figure out what to do. Have your what-if plan already there, and the contractor knows what it is, and things move a lot faster. And then have an adequate construction, monitoring, and quality control program. And I want to emphasize this last part because it's one thing that didn't happen on one of our jobs. With required communication between the field and the design office. Got to have that connection between what's being observed in the field and the design office. And then assume but verify. There's lots of things you're going to have to assume. Verify them. If you can't verify them for some reason, then steps 6, 8, and 9 are even more important. Okay, this is the case histories that we want to talk about, and they're all there. We'll go quickly to the first one. And this one I'm using to illustrate maximizing the bearing pressure, and there's a unique feature that helps us get to that maximizing the bearing pressure. But it's a 65-story office tower built where a former belt caisson supported parking structure had existed. This is what it looks like. It was right next door to a 10-story footing supported building on soft clay that had already settled 4 or 5 inches, and rather scary right by itself. And now you've got these huge caissons that have to go in alongside of existing caissons that were stopped in the hard pan. And how do you get them in? Well, in some cases you actually could fit them in. There are a number that could be fitted in. But because there are a number that couldn't be fitted in, then we looked at, well, maybe we got to go to rock. These are, I think it was 14,000 kip column loads. So not much alternatives to going to rock socketed caissons. Again, we have found in our experience that rock-socketed caissons cost about triple what a belt caisson solution would cost. So there's tremendous pressure from the owner and developer. Can't we do something other than go to rock? So this was a case where we looked at it and we said, well, if we can dewater that underlying silt, that water-bearing dense silt that underlies the hardpan, if we can dewater it sufficiently so that we can go down and bell there, that bearing stratum is better than a hardpan. The pressure meter test data in that stratum was better, and so we said we'll design that for 50 KSF if we can dewater it. And so we had some limited success with using filtered dewatering wells to lower the water head. And so we said, well, if we can use filtered dewatering wells, lower the water head so that we don't have a blow in our face when we construct these bells, we can do it. And so the owner and developer decided, because of all the money they could save if it worked, that's the direction we would go. And then the question is how many wells does it take and so forth. In this case, we had thought maybe we could do it with 3 wells. We were very fortunate because we had a very porous deposit. The reason we knew it was porous is because one of the boreholes lost 100% drilling water. That's the kind of location you want to find if you're going to use a filter dewatering well and you hope to lower the water table. You got to get water out of the ground to lower the water table over a sizable area. You know, if you may lower the water right where you are with a little bit of water, but you're not going to lower it over a large area unless you get a lot of volume. So, how did things work out? It worked out very well. The predicted settlement that we were working with was about 0.9 to 1 inch for these caissons that were constructed either on the dense silt or the hard pan. And they measured the settlement when the dead load was totally on, but the live load wasn't on yet. And the measured settlements averaged less than 0.6 inches. So they were a little less. If you extrapolate out to 100%, maybe they would extrapolate out to 0.8 inches, and we had been predicting based on pressure meter testing 0.9 to 1 inch. So everybody was very happy with the performance, and obviously the dewatering worked. Risk versus cost evaluation. Well, the innovative aspect here was the filtered dewatering to temporarily lower the water table to permit belt construction and water-bearing silt at a maximum bearing pressure determined by pressure meter testing. The risk was, one, that it wouldn't work at all, of course, but also, even if it worked, the number of wells required, the judgment required to estimate the number of wells required for realistic cost comparison. And here, we had to make that judgment call, and we picked 3 wells. And it was because we knew we had a permeable deposit. If we could get water out of it, we'd had enough experience in Chicago that if you can get water out of the deposit, you can lower the water table for several blocks around your site. This is what should you say you're proud of something? I'm kind of proud of this one, but when you look at it and you say 38-story office building built on belt caissons that had supported an 11-story building. Then you might say, how on earth could you put a 38-story building on an caissons foundation for an 11-story building? Is it super light? No, it's a normally heavy structure. So how did you do it? How did we do it? Well, we thought about it, and we used the fact that it had deep basements. It had, I think, 3 or 4 basements, like down about 37 feet. And we realized that when they made that excavation, took all that soil out, that soil below that level was pre-consolidated at least to that level. So we put a mat on that old slab that was there, on top of those existing caissons, and then we shared the load between the mat and the existing caissons. We ought to be able to really up that capacity. And the question is, well, how high could you go? Well, you've got all of that excavation. Now you got almost 40 foot of overburden around you. We had calculated based on, I think, we calculated what the settlement would be at the creep pressure for the existing caissons, and because we didn't want to have to go much over that, and it was about 1 inch. So we based everything on about 1 inch settlement. And how much load could you put on the mat just by itself without the influence of the existing caissons and only get an inch settlement? And in a simplistic way, you got to do some adjusting for the overlap things, but in a simplistic way, you got what the mat can carry to produce an inch settlement and what those existing caissons carry to produce an inch settlement. Put them together, and it was a 38-story building where you only had an 11-story before. So how did it work? Well, here's the diagram that shows the properties. Let's see. Well, you can see some of the properties. The medium to stiff clay, we're below the softest clay with the mat. We're now down into medium to stiff clay. And then below it, we've got the very stiff to hard clay. But it's not good hard pan. It really isn't good hard pan. The existing caissons were designed for 16,000 pounds per square foot. Now, granted, it was built a long time ago, and I was surprised. That's what we calculated based on the load that we were given. They should have only been designed for 12,000 because it was built back in the 12,000 pounds per square foot days, but we calculated it was about 16,000 on it. And you can see the modulus values in the below. Those are maybe 2.5 to 3 times the modulus values in the medium to stiff clay that's supporting the mat. How do we do it? Well, I already said it, but I'll say it again. Using the pressure meter data, calculate the maximum sustained load that can be carried by the existing caissons without exceeding the creep pressure. And that was a settlement of about 1 inch, remember? Calculate settlement of that load. Calculate pressure the mat can take for equivalent settlement. Combined loads at equal settlement represents the maximum sustained building load that can be applied. That's a simplistic story, but basically that's it. Now this is the foundation plan. And this was complicated by the fact that one corner of this old structure had rock caissons. Why it had rock caissons, nobody knows, and there might have been some reason why they couldn't put bells there out in one direction or another, but they had 4 rock caissons on, what would that be, the northwest corner of the building. And the rest is all bell caissons. And so you knew you were going to significant differential settlement. So we had given the structural engineers some spring values based on the the properties of the soils that he put into his mat program, and he said, well, geez, this is I'm going to have to stiffen this thing up, and he couldn't stiffen it up by increasing the mat thickness because he needed all the space for the car parking. So he stiffened it up by using those walls, and he did it in such a way that he could still use cars and things like that. So I thought that was fairly ingenious of him to come up with a plan that he didn't have to thicken the mat. Observed settlement. How did it work? Well, at the time, one of the things I found, some of you can appreciate this, it's tough to get people to pay for settlement measurements. Nobody wants to pay for it. They don't want to know if it settles. If it settles, okay, then they'll hire somebody to find out, well, how much did it settle? But so we had we couldn't get anybody to do the pay for the settlement. We ended up paying for the settlement measurements ourselves, just because we were that interested in what the settlement was. So we only got a one-shot of it. Cost does have a factor. And it was with the building, and all the dead load was in place, it was all up, but the live load wasn't in yet. So we would estimate maybe 70% of the total load was on. And the predicted settlement then would be about 0.7 inches. Remember, we'd come up with 1 inch for the total, about 0.7 inches. The measured settlement varied from 0 inches on the rock caissons to about 5/8 inches. Now, allowing for some survey accuracy, maybe you'll say, well, it's got to be more than 0. Let's say it's 1/8 of an inch to maybe 3/4 of an inch. So maybe that's the range of settlement. But it's right on target for what we had predicted. And it's all based on the pressure meter testing. Risk versus cost evaluation. The principal risk was under-predicting settlement. Existing caissons would be pushed into the ground with pressures exceeding the creep pressure, making them like settlement reducers. Suppose the mat, there wasn't that much resistance for the mat. All that building load just pushed those old caissons into the clay. Then they would have exceeded the creep pressure. They would have acted like settlement reducers, and all. But the thing wouldn't fail. So all we would have is just more settlement than we predicted, which would create a problem because of the rock caissons. So we're darn lucky that it behaved like we predicted and not worse. Or then we would have been stuck with what I would call, what was your plan B if you were wrong? Well, you'd have to go in there and do put in some micropiles. We got micropiles here at the right places, or maybe it's more stiffening walls. You would have to you'd have to spread out that differential settlement. The judgment was that the value saved by this combined foundation design was worth the risk. And everybody was very happy with the way the project turned out. Now we come to 2 value engineering projects, not so big, just barely make I think we set 12 stories as the high-rise criteria in our town. And this is supposed to be 12 stories, actually built 10, but you can see where the top two were, it's going to be 12. And then the second one is actually a 20-story, I think. But in this first one, there was an initial geotechnical engineer who had done the investigation and observed there's no hard pan here, and he was right. So he had come up with, he said, and if you use footings, because it's very soft clay in this part of town, if you use footings, it's going to be like 8 to 10 inches of settlement. The owner wanted to use footings because there was a nice dense sand layer on top of the soft clay, and smaller buildings would work fine on that sand layer. So why couldn't he do that? Well, we got called in. The structural engineer recommended to the owner that we get called in and look at if there isn't some other way to reduce the cost, because it was all, the project was budgeted on either footings or belt caissons. That's the way they had budgeted it, because that's what they were expecting. And belt caissons couldn't work because it wasn't the hard pan, and the footing situation gave too much settlement. So we had the concept, well, suppose we combine footings with straight shafts under the columns that would serve as settlement reducers, and we took those straight shafts down, there isn't any hard pan, take those straight shafts right down to that dense silt layer. And we had had some experience. If you had the concrete standing by and you drilled the shaft down, you dumped the concrete in before the bottom loosened up too much, you were in good shape. So that was we were asked to look at that concept. Could that concept work? And we did some additional investigation, some pressure meter testing, and we got some Oster examples for consolidation testing. The end of the story was that we also agreed with the original geotech that the 8 inches was probably the right settlement magnet to expect if you just put it on footings. And while we do have historic structures, as we already mentioned, with a lot more settlement than that, modern people don't like to think in terms of 8 inches of settlement. So what kind of settlement would we get if we used this straight shafts down to the dense silt under each of the columns? And we had predicted it would reduce the settlement to 2 to 3 inches. That would be using much higher load on that dense silt than the allowable would ever be, but we weren't using them. They weren't necessary for safety. Their only purpose was to reduce the settlement. And we had calculated a factor of safety of just about 2 for the footing foundation case by itself. The nice dense sand layer, I think the next slide may show it here. Yeah, the dense sand layer, there it is. The medium dense sandy silt, and then a stiff, very stiff clay crust. So you got quite a thickness there before you get to the soft clay. So we had calculated about a factor of safety of 2, which in our approach meant that we could design these shafts as settlement reducers. And the only problem is if you're going to use them as settlement reducers as bearing piles rather than friction piles, now it depends how are they going to behave in bearing. That's very important. You don't want to have a sudden failure, collapse, boom. That changes everything. So you want to have a situation where it's strain hardening, not strain softening. So the dense frictional material, it doesn't drop off and load. You may push it into the ground, but you actually get increased resistance as you push. So we weren't concerned about exceeding the creep pressure and maybe pushing those babies further into the ground. They weren't going to suddenly lose their capacity. Now, if it had been a hard clay, where you exceed the capacity of the clay, you could have a sudden drop off. So you got to be careful if you want to use this concept in this way. Now, in another project later on, you'll see a case where we used steel piles to rock as settlement reducers. It's a case where we were very confident, because you're using a high yield steel, so that you can take quite a bit of compression to get those values up there. And for reasons we'll see, we felt that would work. Additional requirements for use of piles as settlement reduces. We already mentioned the factor of safety of 2. The other thing is, because you may not be exactly right in how you think it's going to distribute load, I mean share the load between the footing up here and the straight shaft, the structural engineer must be able to design the footing or mat for the range of possible support conditions estimated by the geotechnical engineer based on the confidence level of the predicted stiffness values. And so we'd worked with the structural engineer before, and we worked together on what range he should use, and that's where the confidence in each other is important. Now, because we only had one boring with pressure meter testing, and I said, we can't just base it on one boring or pressure meter testing, and we had a problem with getting more for cost reasons, time reasons, and so forth. We said, okay, let's attempt to correlate the pressure meter data with all the standard penetration test data that we have in this zone. And the standard penetration tests in the boring with the pressure meter were higher than the average standard penetration tests in the deposit. So we backed down we used the standard penetration test as kind of an indicator, and we backed down the pressure meter values to be consistent with the average across the deposit. And then, in addition to that, we backed it off a bit more, and this was a judgment call on my part, to allow for some loosening. If we couldn't get the concrete into the hole quick enough, and there was some loosening, and it didn't tighten up totally, when they put the concrete back, we estimated what that loosening was. It worked out very well. I'll tell you that. It worked out better than we could have anticipated. And in fact, we probably did not have to do any reduction in the pressure meter values at all. We would have been right on what we predicted, 2 to 3 inches of settlement, if we hadn't reduced the pressure meter values. The actual settlement, this is after 4 years, and there's an interesting feature I'd like to mention to you. Column B6, we instrumented 2 columns, B6 and C2. B6 is at the end of a footing, and C2 is in the interior. C2 is more heavily loaded, and normally you would expect that would settle more. The end column, more lightly loaded, settled more. Now, if you think about it a little bit, it makes sense, because the end column only got the footing support on one side, didn't have the footing support on the other side. The interior column had the footing support benefit in both directions. So, as a result, the end column one, the bearing pressures below there went up to 76 KSF in that dense silt. In the C2, in the interior one, where the settlement wasn't as much, it only went up to 48 KSF. But in both cases, it's well below the 2 to 3 inches we had been basing everything on. And even when you add 2 stories, now there's only 83% of the load on, so you got to project these up for the added 2 stories. They still haven't put the added 2 stories on, however. Now this is the one I wanted to tell you about, where we, you don't like to tell. We expose your dirty linen, I suppose. But on the other hand, you should share your experience so everybody can learn from your experience. So this is a case where it didn't go as we thought, and where we had taken some. We didn't follow all of our own guidelines as well as we should. And I was really involved in this one, so I got nobody to blame. Let's see. There's the. By the way, this was a value engineering job, a value engineering idea from the contractor. So we were called in after there was original geotech that we're going to go to rock socketed caissons, big price, and the contractor came along with a value engineering idea. I can save you a bundle if we just go down a straight shaft to the top of rock. And we, instead of using 100 TSF, which is the code allowable for sound rock, 1 foot into sound rock in Chicago, if we just go down to the top of rock and we'll cut it in half. We just use 50 TSF, straight shaft. And he apparently came up with a price that really attracted the developer. And so we were called in to validate it. Is it possible? And we said, well, if we do a pressure meter testing on that interface, we may be able to verify 50 TSF to the satisfaction of the city. The city is the one that had to be satisfied because there's no code provision for sitting on the top of rock. As my pile friends would say, if you'd driven piles, every pile is a tested pile. You know, you'd know what you had. You got a tested pile. But in this case, you know, you're sitting on the top of this surface of this rock, and you don't have any code allowable. So we did do the pressure meter testing at the interface. We did satisfy in our own minds that if you got down inside of the surface of the rock, 50 TSF had a factor of safety of at least 2, which satisfied the city, and the project went forward. Now, if you look at this, these borings are all around the perimeter, and it looks, everything's flat line, right? Now, the next slide, there was a building in the way in the center of the site, so no borings were ever taken in the center of the site. And so what happened, because we had a new caisson inspector, never done, these shafts were all done under slurry, and so he'd never done a slurry caisson before. And so I went out the first day and showed him how to, the caisson contractor had done slurry caissons before, so we were working with an experienced contractor, what to look out for. We didn't have a mini SID like you have down here. We do it by sounding, make sure that they got the muck bucket has cleaned it up enough. I wish they'd used an airlift, but they do it with a muck bucket. And you can sound with it. If the sounding thing sticks, you haven't got enough of the stuff removed. Anyway, we followed the procedures that we had been successful with in the past, and you know, the only problem is the contractor had given his estimate on the assumption that he could auger refusal would be the surface of rock. And in the first 2 shafts out there, fortunately, we had borings near the first 2 shafts, and we weren't down to the rock. So the contractor agreed. Okay, yeah, well, I know we got to get to the rock. We'll put on a rock auger, and we'll switch to a rock auger, and we'll go until we're close. We're at the right elevation based on the adjacent boring. Well, and the 2 that I was there, that required 20 minutes of rock augering. So I told the inspector, you follow the same procedures on the rest of this job. Make sure they don't try and stop with just auger refusal. They switch to the rock auger and they grind away for additional 20 minutes. And if they get 2 to 3 feet deeper with the additional grinding, that should be okay. I didn't hear from him until almost the end of the job, and he called in. And I asked, well, how'd the job go? And he said, hey, the job went fine, except as we moved over into the center of the site, the rock seemed to rise, and the shafts got shallower and shallower. And I knew immediately that something's wrong, because I knew the area pretty well. It just wasn't likely. So fortunately, the quality control program that we had set up, and here's where you can catch things with a good quality control program, it allowed the geotechnical engineer to pick 2 caissons to core all the way down through, make sure what you got. So obviously we picked the 2 shallowest ones, the one that stopped the shortest, and they cored it, and they were 5 foot above rock. 5 foot above rock. Well, what had happened is there were boulders there, and they hit some boulders that were sufficient to even stop their rock auger, which is, well, stopped the rock auger with only 20 minutes of rock augering. Now, they tell me that now they've learned. We learned on that job, and they tell me they've learned too. One thing they learned, if they think they got refusal, maybe they put on a core bucket to make sure they're in the right thing, or grind away for a lot longer. We were on some jobs where they ground for 2 hours to get down with a rock auger to get down to the level where the borings indicated. The problem here is the poor inspector didn't have any borings in the center area to guide him, and his common sense said, well, I used the same procedures that Clyde told me. I'm following the same procedures that Clyde told me. And so the rock must come up. So anyway, we did a lot more pressure meter testing. You get the whole job's in, right? All the foundations are in. A lot of them are 5 foot short of rock. What do you do? They're on refusal, rock auger refusal, but what do you do? So we did a lot more pressure meter testing. We did a lot more analysis. And we worked with the structural engineer again very closely, giving him spring values. He ran it through all of his finite element programs. And he concluded that also that we were probably okay, except he had set a criteria, column to column, he couldn't take more than 4/10 of an inch settlement. And based on the spring values that we gave him, he had one place where it was more than 4/10 of an inch, so we had to do some micropile supplementing there. But generally speaking, it went forward like that. Now, I should mention that the way we got it through, I mean, because we did the pressure meter testing right under these shafts, it wasn't 50 TSF material, because you can't test boulders, you know. So we're alongside the boulders. The boulders actually probably supported the glaciers. They're right alongside them. It's not as hard as it is without the boulders. So we had we didn't have 50 TSF material, but it was close. It was like 30 TSF material. And we convinced the city that, well, the side friction would probably take care of it, but the city doesn't allow you to use lab testing and things like that. They want a full-scale physical test. So we got them to accept dynamic testing and with CAPRAP analysis. So they dynamically tested with CAPRAP analysis, and we got a friction value for the side friction, and then we took that load off the end bearing and got it down to less than 30 TSF, which was what we were saying, the pressure meter was saying was good for. Now, it was probably okay because the boulders were there, you know, and everything, but you still got to prove it to the city. So that's the way we proved it to the city. The city let us go forward like that, and it worked out pretty well. This is a picture of what it looked like, the settlement. The first 9 floors, we figured very little settlement is what's being carried in friction. From 9 to 12, there's a drop in it, and you know, we figured that's we didn't have the mini sit, or we didn't, you know, we have probably left a little stuff in the bottom that's squished, and so there's your squish. Now you're bringing your boulders into contact, boulder to boulder. Stress path goes down through the boulders to the rock, no more settlement. So from 12 stories to 20 stories, there's hardly any settlement. So in the end, the project worked okay. It stayed out of court. I don't even want to talk about settlement because it's, you know, it's a happy history, and it stayed out of court. What were the risks and important lessons? Well, things are not always what they seem. That's a good one for my inspector and me. Incomplete communication between the field and office can lead to major problems. A normally adequate subsurface exploration program may prove insufficient for a change design based on value engineering. Well, I would say we probably should have had done the center boring there in any case, but certainly for the changed value engineering design. Key assumptions must be verified. It's one of our things. And the good thing, a quality control system that included physical verification of assumptions can find mistakes or defects before foundations are loaded and built over. And I would also add that I think getting a principal involved, you know, right away, so decision making can go quicker, and the client thinks he's getting the top information he can, helps avoid liability problems. Now this is the next to last case history. This is a case history that has everything, all five things: maximizing the bearing pressure, mixing the foundations. Let's see. use of piles of using existing use of existing caissons, use of settlement reducing piles, and a remediation plan. It's built on a site where we were the original geotechnical engineers 40-some years earlier. Yeah, at least 40, almost 50-some years earlier. That was on belled caissons. At that time, the design bearing was before the pressure meter. We came up with a design bearing value of 16 KSF for those belled caissons. Building was raised in 1996, but they saved the three-level basement, and then they wanted to keep the basement, and then they built this 51-story office tower on the same foundations, supplemented with a mat and new deeper caissons. That's what was done. And this is a picture of the caisson plan. You can see the existing caissons. Existing caissons, like they're all those dark ones, are all the existing caissons, and then these are the new ones. And the new one, obviously, they can't go at the same level. The new ones got to go underneath the others, and that involves, going to a deeper bearing level. You got a higher capacity zone down deeper. You got the shallow. You got and you're mixing things. But the key is, can you predict performance? Can you predict how the upper level existing caissons are going to deform? And can you predict how the higher capacity caissons are going to perform? That's the key. Now, if you look down at the base here, these are two problem ones that developed later. And we talk about those. They got too close to existing rock caissons, and they had a lateral blow-in. One of the lateral blow-ins was bad enough that they couldn't complete it at all. It had to be converted to a rock socketed caisson. The other one was completed sufficiently. Just questions about the softening of the ground, and so it was supplemented with 14 micropiles. And those micropiles we did not have to load test. We were able to convince the city that we were using those micropiles as settlement reducers. Based on the high yield steel, they could settle a couple of inches and still carry load without failure. So we convinced them that didn't need a load test, and you'll see when we look at the settlements that everything was almost as predicted. Well, there's not time for you all to catch a mistake here, but I'm going to point it out to you in case somebody's very sharp. These, somehow or other, the net limit pressure and the creep pressure symbols got reversed up here. The creep pressure is really the closed circles over here at about 12 TSF, and the what we call the creep pressure is really the net limit pressure, is more than double the creep pressure. Those of you familiar with the pressure meter will know what I'm talking about. Then over here we've got the actual old bearing level on the hard silty clay, where it was designed at 16 KSF. Pressure meter testing confirmed that it could go to 24 KSF. And down here at the new bearing level, the bearing pressure for the new hard pan caissons was 45 KSF, all based on pressure meter testing. And then we did the analysis to see what they were going to settle. That information was plugged into I don't think we used finite element at that time. We just used a program that told us how the stresses overlapped and what the ultimate settlement was. I think the primary principal on that project is here. Bill Alton, who's our top guy now, he was the principal on this project. So if there's any questions, you have to ask Bill. Let's see, what are we up to? Okay. Problems, well, we already talked about the remedial action that we did, and that seemed to work well. The settlement prediction and performance. The settlement, as I've said, the elastic settlement, theory settlement, was a little bit more than what we would predict using the Menard's method, but they were all reasonable, all pretty close to what was actually measured. In fact, the one place where the measured settlement actually was greater than the predicted settlement was the isolated caisson that was converted to a rock-socketed caisson. The only explanation for that, let's see, which one is that? That's this one here. The only explanation for that is there must have been a seam or something, because you wouldn't expect the rock-socketed one to settle anything like that. So there must have been a seam there. But the others, the Menard's method for the core mat, predicted settlement 0.5 inches, measured settlement 0.5 inches, and you know all of these are pretty close here. Here's one that's predicted is quite a bit higher than the measured, but all in all, you know, not bad. So this one ended up being a very successful case that really covered all the bases that I was talking about tonight. I'm going to get to the Petronas Towers Revisited. This is the last one. I added this because I actually wanted to revisit it, look at it again. And one of the questions that I've had is, how could we have over-predicted settlement so much when we had so much testing? That was one issue I wanted to look at. And the other was, as I was looking at all this data again, is I had an idea for saving millions of dollars, okay? And I think, well, I'll throw it out. Saving millions of dollars, everybody's interested in saving millions of dollars. So we'll look at that. We'll look at how come it settled how come it settled so much less than predicted? And we'll look at money-saving idea, saving millions of dollars. Yeah. This was a very challenging job. I mean, I love this picture. You know, you can see it was at the time the world's tallest building. They never found the bottom here. This is over 200 meters deep. It's limestone, it's karst topography, limestone with cavities. You hear in Florida, you know all about limestone with cavities. And so, you know, I can include it in our theme here with the concept that this required a remediation plan up front, not after the fact, but up front. We had to remediate this so that we could put these towers here, and the criteria was no more than a half-inch differential settlement across the mat. From one side of the mat to the other, no more than a half-inch differential settlement. And everybody agreed that that's going to require doing grouting. And then the question is, how deep do you grout? Well, the textbooks would tell you that, well, when you get below the point at which the new load is less than 10% of the overburden pressure, the stress effects are insignificant or something like that. And we decided, well, we'll be twice that conservative. We will grout until the theoretical stress increase from the structure is less than 5% of the overburden. So that required going quite deep into the limestone, and we grouted enough. The total volumes were quite impressive. Under Tower 1, the total volume of grout was the equivalent of a 1 meter thick mat that's the total amount of voids that under that entire mat. 1 meter thick total grout. So we're glad we did it. Just a nice picture. That's fun to walk through right there. You know, I think those of you who know about it, one end of that connection is telescopes into the building. So when the buildings go like this, one end is free to flex. Whoops. Here we go. Well, we've already talked about. Oh, that's interesting. World's deepest ground improvement, up to 530 feet. We grouted. That's pretty impressive. And well, the concept, the design concept was using variable length piles under the mat to minimize the critical differential settlement. And we had to predict the settlement based on the modulus values, based on the board pile load testing and extensive in situ pressure meter testing. We did simple equivalent footing approaches before we used the finite element program. And then we also planned to monitor the settlement load distribution, which did happen. It did get monitored. Now, the equivalent footing, you know, you might say, well, why would you use the equivalent footing approach here when you got a sloping rock like that? You really can't. Well, you can only in the sense that you get an approximate average settlement value. We did do it, use the equivalent footing approach. and to calculate an average approximate settlement. And we also sometimes, we didn't on the design time here, but we have on a number of other jobs, we look at this as a rigid block. In other words, you've got a rigid block in our simplistic thinking. You've got a rigid block with a perimeter friction, and then you've got bearing under your block, and you analyze it that way. And in hindsight, if we'd analyzed it that way, with using a friction value with a factor of 1.5 to 2, reduced by that amount to allow for creep and so forth, we could have been right on the money. You know, you could always do a hindsight calculation that will give it to you right on the money. Now, we're running out of time, so I'm not going to give you all of the calculations here. Here's the finite element program with the maximum settlement of about 70 inches. 70 millimeters, excuse me, 70 millimeters. And here's the observed settlement, okay? About 30 millimeters, 30 to 35 millimeters. Half of the predicted settlement, okay? So, now one of the questions is, what are the explanations? Well, in the original papers, we speculated that the hard layers, you know, this is a weathered rock, you got relic rock structures, and the hard layers have a bigger influence than you just get from the pressure meter testing. And that seemed like a possible explanation. Then these are others. There's a pre-stress effect of the barrettes installed before excavation. It wasn't considered. And you'll see from the settlement curve that I'll show you that it's quite logical that there was some pre-stress effect. Another possible explanation is faster than assumed stress spreading. Who says M.ASCE got the right number? If you do the rigid block analysis with the perimeter friction, you can come up with the real right number. Another explanation, this is probably one everybody can agree with, that proper soil model is likely nonlinear, and there's increased stiffness at smaller strains. Well, once you accept that, then using an approximate modulus is going to overpredict the settlement by definition. Okay, we've got just 5 minutes to consider the hindsight evaluation of a cost-saving foundation engineer, which on this project could have saved millions. This is a multi-million, I don't even remember how many $1 million foundation system. Why not consider piles as settlement reducers and allow much higher concrete stress levels and only slight increases in predicted settlement with reduced concrete cross-sections? Actually, it ended up not being piles, it ended up being barrettes, but it was designed the same way to keep allowable stresses in the normal range. What happens if you do that? Well, if you do that, you're going to get a little more compression in that rigid block, because now you've got higher stress levels in the concrete, so you're going to end up predicting a little more settlement. But since you've got a deposit where you could have used a mat only, the only reason you're putting in the barrettes really is to control the settlement. You've got our criteria, which we said you're going to use a mat only, you should have a factor of safety 2. You probably have it here. Why not? Well, I think the why not is for the next guy. I think if you go back to where we were at that time, and we were right on the nose on the maximum differential, any increase in settlement at all would have blown our criteria. We would have been outside. So I don't think if I brought it up 15 years ago or however many years ago and said, hey, how about this? They would have said, no way. Today, I would bring it up and I'd discuss it with them, the way to save millions on a foundation like this. Okay, conclusions. I hope I've been able to show that innovative, cost-effective solutions to foundation design problems are often possible using combinations or mixtures of foundation elements, provided that the ground deformation in response to structural loading can be reasonably predicted within allowable tolerances, even though geotechnical truth is uncertain and the design ideas are at the limits of foundation practice. The key requirements are geotechnical engineer and structural engineer teamwork, a knowledge of and experience with the local geology and past building foundation performance history, or being more conservative where such information is not available, having experience with use and interpretation of in situ pressure meter testing, or whatever method is used for predicting ground deformation under load in a particular geology. We like the pressure meter, but other people like other things. Having a plan for addressing geotechnical surprises. I think that's a good idea. And then being more conservative when assumptions can't be verified. Thank you.
Mr. Baker, it is truly a pleasure to see how much you enjoy your work. On behalf of the 11,000 members of the Geo-Institute, I wish to thank you for a superb and very practical lecture. This concludes the 2009 Terzaghi Lecture. Thank you.